Hello, everyone. Today, I'm excited to talk about our CVPR highlight poster with my friends and colleagues, Jingshui and Panxu. In the last 5 years, diffusion has been the workhorse of text-to-image generations, and they're extremely good at object and styles. However, they can still struggle with multiple objects with relationships. For example, objects could be merged into each other or placed in the wrong configurations. In general, the spatial relationships accuracy is significantly lower than the single object accuracies, showing the challenge of these problems. So how to study this issue mechanistically? Since many pre-trained models does not have this behavior, then we cannot dissect the circuit of a behavior that does not exist. And then we think we need to train the model to perform well on this relation generation, and then we can dissect it. So to study this problem, we create a minimal setup for learning relational object generations. We create a dataset of prompt and image pairs. This prompt, such as blue square, is above red circles. On the scene, there will be two objects with relationship with each others, with different colors and relationships. And then we train them using the architecture of Pixar DITs with cross-attention, translating text information into image tokens. And then we experimented with different kinds of text encoders. For example, we tried classic choices of CLIP and T5. And we also experimented baselines such as random token embeddings with or without position encodings. In this case, each token ID are mapped to a unique random vector that is fixed. So in this case, the text tokens have no semantic in it. And then diffusion transformer need to figure everything out. So can they learn it? We find even with random embeddings, diffusion transformer can learn this task well. They first learn to create the target attributes like shape and color. Then they're binded correctly for each object. In the end, the correct spatial relationships are imposed on the two objects. And in general, spatial relationships are learned in the last in this training dynamics, showing its difficulty. So how is this behavior implemented inside the models? What circuits mediates this behavior? And how does diffusion model determine position and identity of object? Which one is determined first? So we think we should focus on the cross-attention mechanism, which is a key to translate text into images. So we invented methods of attention synopsis. Basically, we cluster text tokens and image tokens by their properties, and then track the information flow or attention strength between, for example, object 1 and relation words. We summarize this across layer, head, and diffusion steps or time. In the end, we arrive at this table of layer by head, and each entry basically is a score, meaning how much does this attention head mediate information flow from relation words into object 1 tokens. Using this method, we are able to trace the circuit of diffusion transformer. So in the random embedding case, we find the specialized relation head. In this head, the QK circuits basically reads the spatial position embedding of image tokens and also the relation words in the text tokens. As a result, this head will make the top token on the image canvas pay attention to above, and left token pay attention to left. So it translates the textual sense of relation to a spatial direction on the canvas. After that, the VO circuits basically adds a tag to this image token paying attention to the words. This tag, in some sense, basically means let there be object 1. And then there's a downstream object head reading this tag. And the tokens tagged with this label, you pay attention to the first object in the sentence, which is square. And then the tokens without the tag will pay attention to circle. And then the VO circuits will translate the text features of shape into visual feature of shapes, then giving rise to the final image across diffusion steps. How about pre-trained text encoder like T5M clip? In these models, since it's large language models, each words in a sentence can have information of other words. And we find that the diffusion model only pay attention to 2 of the words, basically the last object token and the first object token. We call this semantic concentrations. And to understand how diffusion model use the last object words, we performed a variance partitioning analysis, basically factorize this vector of the shape 2 into different factors describing shape 2, shape 1, color 2, and relationships. And then we can find which relation head basically reads this factor of relationships. We find, indeed, there are specialized relation heads which reads the spatial position encoding and also the relation factor in this final word vectors. And then this relation head will create the spatial gradient according to the meaning of this relation. And then using some downstream object head, it will create this final image. So as a summary, we find the key mechanisms which we call relation head. It translates spatial words of text into a directional gradient on the image tokens. And this gradient basically guides the growth of object at the target locations. Interestingly, this is reminiscent of embryo development, where there are chemical gradients along the body of embryos, and these gradients will guide the development and into different organs along the body. We hope the mechanisms we find will inspire future methods to construct diffusion transformers or build better training algorithms. And thanks for your attention.